Okay, so thanks for the invitation. I will be talking about asymptotics bounded electrical tableau. This talk is based on joint work with David Keating and Istvan Prouse. Okay, so what is the electrical tableau? I'm sure everyone is familiar with standard Young tableau. So electrical tableau is some variant of the standard Young tableau. So if we have a Young diagram and we fill the unit squares in the Young diagram by positive integers, and this filling, the filling rule is slightly different from standard Young diagram. So it's introduced by Cotia and Kim in 2020 as filling the Young diagram, satisfying certain conditions, generalizing both the electrical partitions and anti-electrical partitions. So a partition is simply a weakly decreasing sequence of non-negative integers. And so each partition is identified with its Young diagram. Okay, so if we have a partition consisting of k non-negative integers, that means the length of the partition is k, and then we draw k rows of unit. We draw k rows of unit squares. So the first row consists of number 1 unit squares. The second row consists of number 2 unit squares. Up to kth row consists of number k unit squares. So here is the example. We have a partition 4. Which has length 1, it's just 1 row, 4 unit squares, and the second one is 2 rows. The second one is partition 3, 1, and the first row 3 unit squares, and the second row 1 unit square. And here is partition 2, 2, and we have the first row 2 unit square, and the second row 2 unit square, and so on. So the partition and its corresponding Young diagram are in 1-1 correspondence. So then if we have two partitions, mu and nabta, we write mu is subset of nabta. If the Young diagram of mu is a subset of the Young diagram of nabta. And nabta minus mu, assume mu is a subset of nabta, nabta minus mu is the set theoretic difference of their Young diagrams. So a table is basically a filling of this screw shape by non-negative integers in each unit square. So we know that if the filling is weakly decreasing along each row and strictly decreasing along each column, we basically have a semi-standard Young table. And however, if we change the filling, so each unit square has a coordinate ij, so both I and j are positive integers. Each unit square is indexed by ij, and Lij is the non-negative integer we put in that unit square. If we have Lij divided by n plus Cij, so Cij is the content of the cell ij, which is j minus I. If Lij divided by n plus Cij, this number is weakly decreasing along each row and strictly decreasing along each column, and we call it electrical table. So this n is simply the length of the partition. Okay, so if we have a partition nabta, we consider if we have just a partition nabta instead of screw shape, and n is the length of nabta. And this Cij could be j minus I, could be, could be. So n plus Cij, the minimum value of that is 1. Then if we require that this quotient is always bounded by t, we have this table are bounded by t. We have a bounded electrical table. So here we see a picture. In this case, we have a shape given by nabta is equal to 2, 2. We have a shape given by nabta is equal to 2, 2, and n is equal to 2. And then we have L11 is here. Is L115, L126, L212, L223, and we can see that this filling divided by n plus j minus I, so this number is weakly decreasing along each row and strictly decreasing along each column. Here is an example of electrical tableau. And this electrical tableau are in 1-1 correspondence with non-intersecting paths on a new constructed graph. So how do we construct this correspondence? Basically, somehow we rotate this square by 45 degrees, and we have 2 here, and 5, 3, and 6, and So we have 5, 6, 2, 3, and we rotate this by 45 degrees, and we obtain 2, 3, 5, 6, and here we have n plus j minus I. So then after we rotate like this n plus j minus I is constant along each column, and then here we have 2, and then in the first column we have two squares below, and the 3, 5, and in the second column we have 3 units below and 5 units below, and here we have 6. In the third column, we have 6 units below. This way, we get a correspondence between the electron hole tableau and the non-intersecting paths on a new constructed graph. So this also corresponds to perfect matchings on a bipartite graph. But we can see this the bipartite graph from left to the right it becomes finer and finer, and this bipartite graph is not doubly periodic. Okay, so then from the with the non-intersecting path configuration on this newly constructed graph, and then people consider this graph become larger and larger and contains more and more faces, and rescale the graph so that this graph approximates simply connected the domain in the plane, and then use simulations they get such a limit shape. So we can say there is a curve tangent to the boundary. So outside this curve, we have frozen region. Only one configuration has probability 1 to occur, and the other configuration has probability 0 to occur. And inside this curve, each configuration has probability strictly between 0 and 1 to occur. So they have more freedom. So inside this region, it's liquid region. Outside this region, it's frozen region. So the limit shape is given by naphtha. So this case, the naphtha, the shape, the filling is given by n, and okay, so this picture simulation is given by Keating and Nicoletti. And here is another picture. So this is filling of a Young diagram. The partition is given by n minus 1, n minus 2, 1. And you can see in this case, the frozen boundary is like a half circle, and outside this circle, each configuration has probability either 1 or 0 to occur. Inside this circle, the probability of each configuration is strictly between 0 or 1. Okay, so then people study the correspondence, the combinatorial property of this lecture hole tableau. We can consider this LHN n naphtha mu is the set of all n lecture hole tableaus, tableau shape naphtha over mu, and they define the partition function. So the sum is over all the possible fillings, and the T is basically Lij divided by n plus j minus I. So T is a quotient, and they choose the integral part of this T, and X is indexed by the integral part of T at each cell. And they multiply all those X gives us the weight of the corresponding fillings, and the sum over all the possible fillings satisfying the rule of weakly decreasing along rows and strictly decreasing along columns. And this way they obtain the partition function of the lecture hole tableau. Then Courtier and Kim, they computed they give a combinatorial formula for the partition function of lecture hole tableau if we just have a partition naphtha and this n lecture hole tableau, the partition function is equal to X. So if we assume this lecture hole tableau is bounded by T, so this capital T is less than or equal to lowercase t, so this absolute value of X is the sum of X1, X2 up to Xt, and this is absolute value of X to the power of the Seidel naphtha, naphtha 1 plus naphtha 2 plus naphtha n, and multiply the Schur polynomial. So this partition function indeed has a very nice form. However, if originally we have a filling of a screw shape, this is no longer true. So this is not equal to this screw Schur function multiply some weight. Because of this nice formula, So we can somehow analyze the asymptotics of the lecture hall tableau by analyzing the Shor polynomials. So Cortia, Keating, and Nicoletti, they made a conjecture. They say that if we consider the solution of the Burke's equation, ux plus ui is equal to 0. So u is the solution of the Burke's equation, and then this the solution of this Burke's equation is related to the slope of the height function in the limit shape in such a way. So the imaginary part of u is equal to pi multiply dh dy, and argument to u is pi multiply dh dx plus 1. So this is the rescaled height function. So basically, if you consider the height function of non-intersecting paths, every time it come across a path, the height is increasing or decreasing by 1. And then if you rescale it by epsilon, then you multiply the height by epsilon. Then the rescaled height function, then in the limit, the height function become a Lipschitz function. And then you consider the slope of the limit height function. It is related to the solution of the complex Burke's equation by this way. So major goal of this talk is to talk about how to solve this conjecture. Okay, so the complex Burke's equation is known to be related to the limit shape of certain statistical mechanical models. For example, the uniform perfect matchings on the hexagon lattice. So the rescaled the slope of the rescaled height function is given by argument w negative argument z. So it satisfies the condition that z plus w minus 1 is equal to 0. Zx divided by z plus wy divided by w is equal to 0. The solution of this complex Burke's equation, the argument gives the slope of the limit height function. And then the solution of complex Burke's equation is also known to be related to the scaling limit of standard Young tableau. So however, this standard Young tableau, the corresponding particle configuration form a Gelfand-Tesselin scheme. In our case, if we have a lecture hall tableau, we can associate the particle configurations and associated to the random partitions at each level, but the associated particle configurations or random partitions does not form a Gelfand-Tesselin scheme because it does not satisfy the interlacing condition of the Gelfand-Tesselin scheme. So moreover, we also know that as in the picture before, we also know that so here is the corresponding perfect matchings, but this graph, this bipartite graph on which this perfect matching is defined, is not doubly periodic because we don't have a doubly periodic graph on which a perfect matching is defined. So this is basically not a model that has been well studied before because it has some unique characteristics. So what we are going to do is, so we are going to consider, so at each horizontal level, we are going to associate the configuration a random partition. At each horizontal level, we are going to associate a random partition. Basically, the random partition is that we find the rightmost present edge, and we find how many absent edges to the left it. So this is number 1, and then we find the second present vertical edge and find how many absent edges before it. So this is number 2, and then here we find the third present edge. We find how many absent edges to the left it. This is number 3, and so on. So this way we find the partition. So at each horizontal level, we find the partition, and we are going to consider the distribution of this random partition. And so then we consider the empirical measure. We consider the empirical measure of this random partition. So so we consider the moment of this empirical measure, and we obtain an explicit contour integral formula for the moment of this empirical measure. And it says that although for example, at level y, this partition is random, so the associated counting measure or empirical measure is a random measure, so this should be a random thing. But in the scaling limit, the right-hand side is a contour integral, it's deterministic. So this gives us the limit shape. This gives us the limit shape of this non-intersecting path associated to the lecture hall tableau. And so this is like the two-dimensional analog of low large numbers. So what we are going, the method we use to obtain this is we are going to define a Schur generating function associated to the non-intersecting path with respect to the lecture hall tableau. So this Schur generating function is basically the expectation of S nabta absolute value of x plus u divided by absolute value of x. So absolute value of x is x1 plus x2 plus xt. So if we consider the expectation of this quotient, this gives us a Schur generating function. Okay, so then we use a differential operator acting on this Schur generating function. If we use a differential operator acting on this Schur generating function, this gives us exactly the expectation of the jth moment of this counting measure to the power m. And then we use the Schur branching formula. We show that by a Schur branching formula, we show that this Schur generating function is indeed independent of this level kappa. So at all level kappa, the Schur generating function are always the same thing. So the Schur generating function at an arbitrary level is the same as the Schur generating function at the bottom level. So at the bottom level, we have the partition is nabta 0 with probability 1. So this is equal to S nabta 0, absolute value of x plus mu divided by S nabta 0, absolute value of x. And then we analyze the leading term. We show that the expectation of the square of the piece moment is approximately the square of the expectation. That means its variance. That means its variance is 0, is approximately 0. And that means, so in the scaling limit, it becomes deterministic and no longer random. So the frozen boundary is a boundary separating the frozen region and the liquid region. So how we get the frozen boundary? So basically, we consider so it is known that the density of probability measure is related to its Stiegis transform by such an explicit formula. And if the density of the limit counting measure of the partition is either 0 or 1 at a point, then the point is in the frozen region. Otherwise, it is in the liquid region. Okay, so the frozen boundary is the boundary of the frozen region because we can already compute all the moments of the counting measure. And then because we already know the moments of the counting measure, then we can compute its Stiegis transform. If we compute the Stiegis transform and consider imaginary part of the Stiegis transform and take the limit, and we get the probability measure, and we find when we get the density of the probability measure, we find when the counting measure is 0 or 1, we find the position where the counting measure is 0 or 1, that's frozen region. And if the counting measure, the density of the counting measure is strictly between 0 and 1, and that's in the liquid region. This is how we identify the liquid region and the frozen region, and then we can find the frozen boundary. Okay, so here is a picture of the frozen boundary we draw. So with bottom boundary partition is given by like 2n minus 2, 0. And the weight function is it changes continuously. And then we can prove the conjecture by Quartier-Keating and Nicoletti. So assume G is uniformly weighted such that S is equal to 1 minus Y. So Z plus is an explicit diffeomorphism from the liquid region to the upper half plane. And then SM0 is the moment generating function of the partition given at the bottom boundary. And if we define U is given by this, then U is you satisfy the complex Burke's equation Ux minus UUy is equal to 0. And the argument of U and the imaginary part of U is related to the slope of the limit height function in such an explicit way. We may also consider the height fluctuations. So when we obtain that limit shape, we consider this rescale height function. That means we rescale the height function by the same factor as we rescale the graph. If we multiply the mesh size by epsilon and we multiply the height by epsilon as well. However, so for the height fluctuation and the Gaussian free field, basically we do not rescale the height function. We consider unrescaled height function. We can show that the unrescaled height function converges to the Gaussian free field in the liquid region when the bottom boundary condition is piecewise. Basically, the bottom boundary condition is given by all particles here. Hold here and particle here and hold here. So the bottom boundary can be divided into finitely many distinct intervals, and those intervals are alternate between all particles and all holes. So because we can already compute the moments, all the moments of height functions, if we can verify that those moments satisfy the Wick's theorem for Gaussian distribution, and then we obtain that the fluctuation is Gaussian. But why is Gaussian free field? We still need to compute the covariance if the covariance can be expressed as the integral of the Green's function. And then that means its covariance still satisfy the covariance given by the Gaussian free field. It has such a covariance, and it is Gaussian, its fluctuation, its distribution is Gaussian, then we obtain Gaussian free field. So we can show that the liquid region is mapped to the upper half plane by an explicit homeomorphism, and this height fluctuation is a pullback to Gaussian free field in upper half plane. Okay, that's all I want to talk about. Thank you.
Thank you very much. Are there any questions?
Thanks for the talk. Do you know if there is some way to encode your Tableau or some information about your Tableau into a determinantal point process?
Some information about Tableau and
yeah, if you can associate some point process to the Tableau which will be determinantal.
Oh, yeah. So you have a table which is the filling of the Young diagram by integers, and with this table you can associate the non-intersecting paths, and then you just consider here are particles and here are holes. You have a particle configuration. Does that answer your question? So those present points. Those present by the non-intersecting paths, you have particles, and otherwise you have holes. The starting points are fixed, so this partition is fixed by nabta. Okay, if we just have originally we have Young diagram nabta, then this boundary condition is given by nabta. If we have screw-shaped nabta over mu, so this boundary condition is given by nabta, and that boundary condition is given by mu. Any other questions?
Are there some other questions? Okay, if not, let's thank the speaker again.